Okay, so welcome to the last lecture in CmpE59. Hopefully we'll be finishing the topic of carbon nanotubes today. We're continuing from the slide where we stopped last time. So continuing with the carbon nanotubes, to overcome the difficulty of performing the thermal conduction measurements due to the problems with the synthesizing and the alignment of the carbon nanotubes to form a network, a molecular dynamic simulation model has been previously developed and proposed in reference 24. And in that model, the authors have the advantage of not requiring a high number of parameters deduced from the experiments, like those in the Boltzmann equation. That model result corresponds very well with the previous results obtained, and they converge to a value of approximately 3,000 watts per Kelvin to conduct the modeling studies. And another tool was also developed to examine the vibration and heat flow problems for nano heat flow in, again, very short distances between the nano machines communicating by means of transferring heat. That was proposed by Regenberg and Neeson. In that, they do molecular dynamic simulation of time evolution, kinetic and heat energy. Now, coming to the use of the carbon nanotubes for communications, the best example would be the implementation of the carbon nanotube radio, making use of a single carbon nanotube. With this application, actually, you're leveraging many of the fundamental phenomena that's taking place at the nanoscale by making use of a single carbon nanotube, as we mentioned. This will serve as a radio for the nanoscale, implementing all features actually of a radio. One of the physical differences for the nanoscale is that the mechanical resonances at the nanoscale are in the range from 50 megahertz to 5 gigahertz. This is actually very useful for us because this range is the range at which our regular human scale wireless devices are operating. Like the cellular phones, Wi-Fi, and most other electronic equipments are already using this range. So we don't consider this as an interference, but we consider this as an opportunity to communicate with the nanoscale using the existing technologies. So the fact that the nanotube exists at the nanoscale implies that it has some mechanical resonances that overlap with the frequency of these daily devices, the current technological devices we already have. So please note that also the resonance frequency is related to the tendency of the system to oscillate at larger amplitude at some frequencies rather than the other frequencies. So at the resonance frequencies, when you increase the amplitude of the oscillation, it does not change the frequency of the oscillation. Rather, it increases the amplitude, thus the energy is not being released through oscillations, but it is actually being stored within the object. Okay, remember the resonance in physics. So at these frequencies, even some small periodic driving force will build up more energy in a device. So it will produce larger amplitude oscillations, vibrations. So the system will be storing this vibrational energy in this way. So remembering the fact that we're using we're able to resonate the nanoscale device. With the technologies we currently have in hand, it provides us a way of communication between the human scale and the nanoscale. So the fact that this overlap between the commercial existing human scale devices and the nanoscale mechanical resonance allows us for a way of implementing the nanotube radio. So there are some unique phenomena within the nanotube that corresponds to the antenna, tuner, amplifier, and demodulator of a radio. This actually defines a full radio for communication for us. The complete system is comprised of a carbon nanotube, which is mounted in close proximity to another electrode, and we're providing direct current to this carbon nanotube and the electrode. So this way we are powering the nanoradio receiver. So when you power it like this, there will be a charge placed at the tip of the carbon nanotube, which makes the nanotube very sensitive to changes in the surrounding electric field. And this will actually provide the oscillation of the carbon nanotube. Since the resonant frequency of the nanotube is in the range of the devices we already have, these devices will cause a change in the electric field, and therefore the carbon nanotube will detect it and oscillate accordingly. So we can tune the nanotube's resonance frequency in at least two different ways. A rough and approximate and non-reversible, that's important, way of tuning would be actually burning part of the carbon nanotube to make it shorter. So you burn the tip off from the carbon nanotube, and the length of the carbon nanotube changes. Therefore, the oscillation frequency changes. So if you burn it such that the frequency matches the frequency you want, then you can use that. But the problem is, since you're burning the carbon nanotube, then you cannot change this frequency, at least not in the reverse direction. Thus, the length of the tube will be reduced, just like the string on a guitar. When you make it shorter, the frequency will change, and it will cause an increase in the pitch. So the resonance frequency of the nanotube will also increase. So the nanotube will act as both an antenna to detect the signal and also as a tuner by varying its length. An amplifier also exists within the nanotube radio, because you actually have a current flowing through the nanotube, which is powered by the external battery we're providing. So the power of the battery is being modulated this way by making use of the nanotube, and this power from the battery is much larger than the signal you're detecting. So it serves also as an amplifier. Since commonly used radio frequencies overlap with the resonance frequency of the nanotube, much of the radio communication engineering is now mechanical rather than being electrical, and it requires a good understanding of how to control the resonance frequency. Okay? So the resonance frequency is shown here, where L is the length of the tube, Y is the Young's modulus, and I is the area moment of inertia, which we'll be talking in the following slides. Rho is the density, and A is the cross-section area. So the area moment of inertia, which is also called the second moment of inertia, actually measures an object's ability to resist deflection. Okay? So do you know what I-beam is? This is just like the rail on the railroads. If you look at the cross-section, it looks like the capital letter I, or if you look at the other way around, depending on how you scale the size, it also looks like an H. Okay? So such a steel bar with a cross-section of I is actually stronger against deflection compared to a similar bar with the same weight, but just with a rectangular cross-section. Okay, so the shape actually also becomes important when you try to resist deflection. This is something that's already being used. It has been known for a long time in civil engineering. So if such a steel rod is called I-beam, with the cross-section of the I shape, an I-beam has higher area moment of inertia than a simple rod of the same mass and length. And that can be thought of as the position along a lever required to stop a force that's trying to turn that lever. So you apply a force on the other direction so that you stop that force turning it. So the farther you're from the pivot point, we all know that the leverage effect you obtain will be higher if you're further from the pivot point, right? However, the notion of the area moment of inertia should be taken into account. It should take into account also the shape of the object. As I said, for example, the I-beam shape becomes important. So each point within the object itself will now start resisting to this turning effect by the external force. But the effect will depend on how far that point is away from the pivot point. So the shape of the object will become important. Okay? If you have a, let's say, steel bar, and you try to, if you have a steel bar, and if you try to apply a force from here, and this finger serves as the pivot here. Now with this finger, actually, I'm preventing this external force. Okay? And the distance between this pivot point and this force that's preventing it is important. If this finger gets closer, I have to apply a larger force, as you know. Okay? But when this thing is, when I'm forcing it this way, actually, the force here for the points here is different from this part. On this side, you have a tension, because if you force it more, it will start shearing from here and break. Whereas on this side, the points here are being compressed. Okay? If you're forcing it this way, these points will try to go away from each other, whereas these need to be compressed, especially if you consider a metal bar. Okay? And those in the middle will actually experience nothing. Okay? So, a simple example of the computation along an object that is symmetric along the x-axis, like consider, for example, a cylinder shape. It doesn't have to be cylinder, but for the sake of the example. Then that can be derived using this equation, where A is the cross-section area of this rod. Y is defined by the, this R should be deleted, by the shape of the material. And I sub x is the resulting second moment of inertia that we need for the previous I here, okay? So that is the resulting second moment of inertia in units of length to the fourth power. You should note that for a cylinder, like this carbon nanotube, for example, the moment of inertia can be computed by pi over 4 times r to the 4 of the outer radius of the cylinder minus r to the 4 for the inner radius of the cylinder. So the thicker the tube gets, the larger the second moment of inertia will be. So from reference 25, we know that the minimum detectable electric field amplitude is shown in the equation which has fallen into the following slide here, where T is the temperature. This is a Boltzmann constant, as you know, and this is the effective mass of the carbon nanotube, and Q is the quality factor, and B is finally the bandwidth of the oscillation. Okay? So the oscillation of the nanotube depends on the portion of the mass of the tube that is actually oscillating. Not all of the all of the carbon nanotube will be oscillating. The part after the pivot point will be oscillating. And the effective mass of the tube is the mass effectively taking part in that oscillation, which correctly predicts the behavior of the system. That quality factor we mentioned here, Q, is a measure of the degree to which an oscillating system is underdamped. If a system is underdamped, we say it has high quality factor. Such a system will expend most of its energy at or near the resonant frequency. On the other side, a system with low quality factor, which means it's overdamped, that will spread its energy over a large range of frequencies as it slowly comes to a halt, rather than keeping on oscillating. And typically, for communication purposes, we prefer higher quality systems. These are more desirable since they pack the energy into narrow and predictable frequency range so that you can just focus on that part and try to demodulate that frequency band. So the energy that's radiated can be found with this formula now.
Sorry,
yes.
What was W0 over there? The angle or something?
That's 2 pi f.
Okay.
Where f is the central frequency there. The demodulation of the signal from an amplitude modulated carrier wave simply requires a rectifier to perform the envelope detection. Remember, when we have an analog modulation, you try to discover the envelope. That's how you modulate your information on that analog signal. And the carbon nanotube is capable of demodulating an amplitude modulated RF signal, like an AM wave, due to its nonlinear current voltage characteristics. And these nonlinearities can rectify a portion of the applied RF current. And the use of a nanotube as an AM signal demodulator has already been described in 26. If you're interested in this topic, you can just go into that. So, in general, one can imagine two very general approaches to nanoscale networking with nanotube or nanostructure substrates. In the first one, you attempt to assemble the network substrate in a precise pattern using self-assembly techniques. That means actually laying the carbon nanotubes in the communication medium in a designed way, in the way you wish. Okay? And the alternative is, since it's difficult to deploy the carbon nanotubes this way, in a precise manner, you just deploy them randomly and then try to work with that random network of carbon nanotubes. We'll first talk about the first one, then we'll come to the second one. The second one is easier, of course, for deployment purposes, but of course, more difficult to handle. So first we will discuss the aspect of the controlled placement of the nanotubes using self-assembly. Since you cannot place them by hand, you have to find a way of self-assembling them in a regular pattern. And we will be benefiting from the biological realm to achieve this. So in the next section, we'll be discussing the impact of communication with the randomized placement of these carbon nanotubes or nanostructures. When you choose not to deploy a random network of carbon nanostructures, You should find a way of now deploying them in a regular manner as you wish. However, the current lithographic printing methods have difficulties in achieving this desired accuracy. There will be too much noise, and there will be, unfortunately, unwanted metallic nanotubes around. So one proposed solution is making use of the DNA self-assembly structure in a bottom-up approach. So this technique is applied, for example, for the computer chip design, but we will see that it has many of the elements of the computer networking to make it work properly. So before going into that discussion, we should now slightly talk about the topic of active networking. Has anyone heard about active networking before? It doesn't have to be, by the way. Active networking is not directly related with nanoscale networking. No one heard of it? The internet, you know, as of today, is not an active network, because it's actually mostly static. It has been designed in a way that computation within the network is minimized. You try to just process the header, which is very short, and with very simple calculations, you understand where to direct it and direct it that way. You don't look at, remember, you don't look at the payload at all. You just look at the simple header. Actually, even in the header, what you're looking at is a destination address typically. Or in the case of MPLS, you look at the label, whatever. But you look at a field that mentions where it should go, that's all. Of course, if you're trying to provide quality of service, you should also be looking at some other fields like type of service, whatever. Okay? But it's, the internet is designed on the idea that routing should be a very simple process. So extract everything out, just look at the header, and by looking at the destination, try to estimate where it should go and design your network accordingly. Then, of course, to maintain the network, you also have to design some complex algorithms that will keep those routing tables up to date and correct. In case of a failure, they should take care of it. Then you have the problems of how you do networking inside an autonomous system, like the Boğaziçi University network, and among or between the autonomous systems. In the concept of active networking, the mindset is completely different. So we will be talking about active networking briefly. So the discussions here about active networking might be beneficial for you, even if you don't want to work on nanonetworking, but if you want to consider active networking. So active networking is a novel approach to design the network now in a different way, in which you have the network nodes like the switches, routers, hubs, bridges, gateways, whatever. For us, these are all routing devices that perform customized computation on packets flowing through them. This time, the packets are now carrying, in addition to regular data, regular information, they could be also carrying some, for example, code. And the code is being processed as the packet is being routed throughout the network. So the packets that the network is carrying can now change the underlying operation of the network itself, defined by that code inside the packets. So this type of networking is called an active network, because the network is now active and very dynamic, and it's evolving all the time, because new computations are now injected into the nodes in the network in a dynamic manner. So the behavior of the network is being altered on the fly as the packets are propagating through the network. So the packets in an active network can carry fragments of the program code in addition to data. And customized computation is now embedded within the packet code rather than the algorithms that are fixed and running on the routers, which is executed on the intermediate network nodes on these routers throughout while the packet is flowing through these nodes. A well-defined framework for such active networks has been proposed in 28 and 29, and the active networks allow processing to be distributed within the network, and each packet can process information that it's carrying inside whilst flowing through that path. So active networks actually are an alternative to the internet, the current internet architecture. Actually, this is under debate. There are, of course, supporters of active networking and also people who are against active networking. But the current internet architecture has the protocols that are built upon the unquantifiable notion of simplicity. The existing protocols try to simplify the routing process so that we can handle billions of packets flowing in the network every second. However, to maintain the proper operation of the network, behind you have to run very complex algorithms to keep those routing tables up to date. Okay, so routing itself is simple. Just look at the routing table, look at the packet, and find the match, apply a mask, find the match, and send it over that link. Routing is as simple as that. The more complex thing is, how do you keep those tables correct? Especially with a dynamic network where the links may go up and down, or links may get congested or not. So the current internet community has carefully crafted many protocols, but these are mostly static protocols or quasi-static protocols, which require a massive amount of documentation on the order of 4,000 to 6,000 RFCs, request for comments. Okay, so it is quite complex actually. One major problem with the existing internet structure is that it's actually quite static, in the sense that the algorithms that are running on the internet at the moment have been designed long ago, and if you come up with a better algorithm, although your algorithm may be better, it will take a long time to deploy it all over the internet. And you should find a smooth transition mechanism, because you cannot call the world and say, next Monday we will be deploying new protocols, so sorry, you will not have internet access for 12 hours. You cannot do that. So you should find a way of having a smooth transition so that part of the internet runs with the current algorithms while you start deploying the new algorithms here, and then the deployment will just spread all around, and hopefully almost all of the internet will someday pass to that new protocol. But even this is very difficult, because most of the time such a transition also requires that you change the devices, the hardware, and not everyone will be willing to do this, at least not at the time you want. That is why actually we have been suffering so much with many protocols. The most well-known one would be the transition from IP version 4 to IP version 6. And we're still in the process of transiting from IPv4 to IPv6. And we have been telling this for more than a decade. Still, we cannot say the world is now running with IPv6. So that is the major problem. You cannot easily do a transition. Or if you're designing a new algorithm, you cannot test it. It's pretty difficult to do tests, because whatever you're doing, you have to do it in a separate network or on simulations. and prove that everything is working. You cannot start doing something in part of the network. So active networking at the nanoscale is an ideal mechanism for handling both the low processing power of these nanomachines and the variability in their connectivity due to the imprecise nature of this self-assembly, especially when they're randomly deployed. Each node in this nanoscale, in other words, these nano routers, you can say, contains just enough capability to communicate and do some simple processing, limited simple processing. So the individual nanoscale components are now connected using, for example, DNA hybridization to guide the connections into the positions. And the processing occurs by creating an active packet which contains data together with some program code. So a communication packet contains now the processing commands as well as the data, where these processing commands, sometimes we'll call them as a code. The packet flows from one nanorouter to another, and each node will perform some limited processing that is defined in the packet itself, and then forwarded to the next nanorouter. And this will require that the minimal processing nanoscale nodes should be capable of doing routing. Here you have two links. One is about a PDF file on active networks. If you're interested in active networks, please have a look at it. It's a very short one. It will just let you get the basic ideas, that's all. If you want further detail, you have to dwell into that. And the other one is the video by Steve Bush, the author of our textbook. So if you're interested in this topic, you can also watch that video. Don't worry, I will not make you watch it now because this is something like 50 minutes. So you can do it offline if you wish. So, I guess we still have time. Okay. So, Avaya, probably you already know what Avaya is from your computer organization or digital logic courses, if you've taken one, especially in the lab. So Avaya, as you will remember, is an electronic circuit. Avaya in an electronic circuit is actually a hole that is filled with some conducting material so that you connect one layer to the other. Like, consider the design of a very simple PCB. You probably have done when you were a sophomore student. You have connection lines on both surfaces of the PCB. But then, at some point, you have to have a connection from one surface to the other. From one layer to the other. So what you do is, you drill a hole, and you just solder a metallic cord in between. That will provide the conductivity so that electric current flows from one layer to the other. That was, remember, called a wire. So the wires are typically used to connect the traditional microelectronics world, could be used for this purpose, to connect them to the nanoscale implementation also. So a transition between the two different layers now. One layer at the nanoscale and the other layer at the microelectromechanics scale. But the wire itself would be large compared to the components in the nanoscale. So one wire may overlap with many nanoscale components. But one of the components will be designated to be the interface to this wire. Okay? Whatever comes through the wire or whatever needs to be sent through the wire, one of the nanoscale components will serve as the interface for this wire. Now, the information, let's say, is coming through the wire. This interface nano node receives it, and now it has to propagate this signal, this information, now to the others. So there you can make use of a reverse path forwarding technique to initialize the routing at the nanoscale first, to set up the routes, and then send the information over those routes. A specially identified broadcast packet now can be injected into the nanoscale network, and that injected packet will propagate, of course starting from the interface just near the via, to the others. And thus, the other nanoscale nodes will learn where the via is and the interface for the via is. Okay? But they should also be able to find the path going to that interface. That also has to be done. So that packet is forwarded by each node along all its connected links. So it's a kind of gossiping. You tell it to all your neighbors except the one through which you heard it. Because anyways, it came that way. So you're gossiping to everyone, and whoever hears from you repeats this process. So the packet will propagate like in a continuous wave throughout the network, and starting from where the via interface is, away from the via, into the network. So this way, actually, you will be establishing the interest of different vias to receive packets. Thinking about the term interest, does this concept remind you anything?
Interest, banking.
Okay, not the interest in banking, in networking. Anybody took the sensor networks course? You took that? Do you remember directed diffusion? Interest propagation?
Interest means what's the interested data of sensor?
The interest would be, for example, the query. So from the sink, you receive a query, and you try to propagate this query to the environment. Here, our interest is coming through the via. The via says, you communicate through me. So you try to propagate this information to everyone. So this is a way of dissemination, actually, of the information. Okay? But you can think of this like the flow of water. And remember, the water will always flow downhill. Okay? Or here it will be explained the other way around, but this is the concept is the same thing, just the other way around. Okay, so we have the information coming through the via, and the via tells it to the via interface. Via interface gossips it to the environment, and the neighbors of the via gossip it to their neighbors. This way, the interest is propagated. Okay? Now, the goal is to establish the way back to this via interface. Okay? Remember, in the case of sensor networks, we were talking about the dissemination of the interest, and also we were talking about the reinforcement in the reverse direction. So it's similar now. So the goal is to establish the directions back to the interface towards the via. So the paths of the reverse flows would look like gradients of a vector field. Or take it this way, just visualize this. You have a water source, and you have a terrain with different heights at any point. When you start pouring water from this point, the water will flow to the part where it has a highest gradient, looking at the slope. Okay? Wherever the slope is highest, it will go that way. That would be your path, actually, for the flow. So it's the same thing here. Now we have the gradients, which shows the slope. So whoever gave you that information first should be the one who is closest to the source. In other words, if I hear this gossip from, let's say, the three of you, but you were the one who gave me that information first, I would say you're closer to the source compared to the others. Because first you told me, I received the same information from the others later. So when I want to send something to the wire, I don't know exactly where the wire is, but I know I should go through you. So I will give the information back to you. Okay? So this would be called a gradient packet. This way I understand the gradient where the slope is highest. That would be the shortest path. Okay? So when a node receives such a packet, a gradient packet, the node keeps track of the link upon which the packet arrived. Like in this case, Sanem was the closest, the first one to tell it. So that it knows where to route the packets to reach back to the wire. And the process will definitely terminate. It doesn't go indefinitely because a node stops forwarding the gradient packets from the same wire once it has forwarded one. Which means somehow if the same packet comes back to the node once again and the label says this is coming from this wire, if you have already seen that before, you don't keep propagating it. So this wave eventually will diminish. That's why it terminates. So upon termination, a tree is created composed of these paths with the wires nanoscale link processing element now becoming the termination point, bless you, termination point for all of these paths. Therefore, it becomes the root of this tree. Multiple wires, one from each of the 4 edges of the nanoscale system, are used to establish the north, south, east, and west gradients. And it is easy to see that the defective nodes and the links will not remain isolated from the final connected system. There will be always alternatives. So the simple route establishment process also removes defective elements from participating. That means it will just bypass those defective nodes and find another path. Okay? So this concept discussed in the topic of, under the topic of active networks is already very similar to what we have been doing for the wireless sensor network. So similar ideas are used in multiple places. A very simple routing technique is thus used to know the up and down routing. Up and down are actually showing the direction. Whether you want to go to the wire or you're receiving something from the wire. So the direction is assigned to the operational links based upon the gradient tree formation that was described in the previous slide. And each link that's closer to the root of the tree, that means closer to the wire, is considered to be up. So it's like the water is flowing, the water is coming through the wire and flowing from the wire. And the receivers are always at lower altitudes. So if they're ties at any point, they're broken by, for example, simply by comparing the node identifiers. You should have a tiebreaker criteria all the time. And a route is simply one such that a packet never crosses link in the up direction after it has used one in the down direction. So, in other words, don't change the direction. If you're going down, you should keep going down. You shouldn't ever turn up. This actually guarantees that you never have routes, so you never have cycles, for example. So this scheme will avoid deadlocks and it will also avoid loops or cycles. And it will also make sure that all connected nodes are reachable. Since this is a very simple method, both the gradient tree establishment and this up-down routing technique are ideal for the limited computing capability of these nanoscale devices. So the trade-off between node complexity and the control of the self-assembly process has been examined in reference 31 again, using a custom network topology generator, a variety of networks that have a varying degree of control over how the nodes are placed and how the links are established between these nodes are examined in this paper. And the system performance is measured by the effects of topology on the system performance. And also the runtime of matrix multiplication is used as a benchmark. And if the processing elements are placed correctly, then there is little variation in performance when you do that matrix multiplication due to the changes in topology, which means it's immune to changes in the topology if they're properly placed. Controlling the placement and also the orientation of the nanotubes has a greater effect on the network connectivity than sharing of the links. And another custom event simulator was proposed in 32 to evaluate the defect tolerance mechanisms. And the reverse path forward algorithm we discussed is applied to map out the defective node in the network at startup of the network. Thus, the defective nodes can be identified, and you find connective paths that bypass these defective nodes. If you look at the current technology, actually there are nanoscale sensors in existence. However, the human-engineered communication mechanisms to transport information from such nanoscale sensors are not yet common. So, in addition to this, also the development of both the biological and engineered nanomachines is in progress. So such machines hopefully will become available in the near future, but then we will need some communication needs between these devices. So conceptually, the information systems in the living cells and the computer networks have much similarity, and in this work we first focus on the analogy between the living self-organizing microtubules and engineered carbon nanotube networks, and look at the similarities in between. So there are some strong similarities, but there are also some differences between the microtubule networks and the carbon nanotube networks. Let me just... In recent work, it has been shown that both the microtubules and the carbon nanotube networks can form random networks, which are capable of carrying information at the nanoscale. The similarity is strong, and therefore, in the following text, we will be using the term nanotube sometimes to mean the microtubules and sometimes to mean the carbon nanotubes. And subsequently, we will be discussing a technique based upon the graph spectral analysis for analyzing a nanotube network. The network graph is extracted from the layout of the tubes, and the ability to route the information at the level of the individual nanotubes will be considered. We'll not go into all details of this. There's more detail in your textbook, but we'll be just talking about the basic concepts there. The impact of the random tube characteristics, like the location of the tube or the angle of the tube, upon the corresponding network graph and its impacts are examined. And the nanotube network and the routing information have important roles in the integral part of the physical layer in the field of nanoscale networks. Since these nanotubes are very small, they are able to penetrate deep into the environment without affecting the natural behavior of the environment. For example, these, we have discussed this before, carbon nanotubes can go into the cells. They may pass through the cell membrane without triggering the cell defense mechanisms. But also remember that there are some concerns about the health impacts of these carbon nanotubes. Individual nanotubes can be used to construct a network of sensing elements, and the depth and the coverage provided with such sensing elements is greater than today's sensor networks. If you look at this problem from a medical standpoint, the alternative to having nanosensors in the body is to have the regular wireless sensors inside the body. But then having immersive techniques to place the wireless sensor nodes inside the human body imposes some risks and it has some unwanted effects. Like, they're first of all bulky in size. Remember, the sensor nodes are typically either this big or there are also smaller ones, but they are bulky. One important thing is it should have the battery, so the battery also adds to the size of it. If you immersively place a sensor node, a wireless sensor node into a human's body, then you cannot use MRI for that person. The reason for having such an implant in the body would be that that person has some health problems. So it is likely that you will need MRI with that person. But once you place that, then that means you cannot use the MRI technique, which is very useful for most medical diseases. So that's a very important problem. Potential radiation damage is yet another one. Surgical invasiveness is not nice, and that will also require some recovery period. And you also need to recharge the battery or sometimes replace the battery. That's another problem. Post-operative pain relates to, of course, the surgical invasiveness, and long recovery times, again, is related to that. And also, even after full recovery, still that person carrying a wireless sensor node inside his or her body will not have a high quality of life in his or her daily life. That will also constitute a barrier in that person's life. So, better and more humane implant communication is required. And the development of both the biological and the engineered nanomachines help in this way. Such machines, as we said, but will require communication. That's something we need to attack. And unfortunately, the networking vast collections of nanoscale sensors or robots using the current techniques, including these wireless communication techniques, is not possible without the communication mechanism exceeding the nanoscale. You can have nanoscale communications inside, but somehow you have to go to the upper layer, to the human scale somehow. So a solution is to use randomly aligned nanotubes, as discussed in 38, for the communication medium. So you will be able to bring the communication that's going on in the human scale down to the scale where you do the sensing, which is the nanoscale. And the biological approach has been well established. Here you have some references. You can refer to those references if you wish. If you look at the current technology, it's focused on mostly utilizing an entire carbon nanotube network as semiconducting material to construct actually field effect transistors, mostly for transistor purposes. And such transistors are typically required to build legacy network equipment we already have today. So the result is that the nanoscale networks are typically embedded within each device, and these may be otherwise designed more effectively, or they can be directly utilized for communication purposes. So rather than using carbon nanotubes to implement these transistors and then go with the regular design using those transistors, what if I have everything down in the nanoscale and try to do communication now among these carbon nanotubes? So you have to think outside the box and rethink the communication architecture based on transistor design, and avoid having the design according to the relationship between the transistors, but have it directly over the carbon nanotubes, which are composing actually communication media. So much research has been done to understand how to align the tubes, but unfortunately, in terms of cost and also due to the separation of impurities like the metallic tubes, which we don't want, we would prefer the semiconductor tubes, is still an unsolved problem. There are some solutions, but the important thing is you should find an efficient way of mass producing these. Lower cost and randomly oriented tubes may be directly utilized as communication media. So rather than properly trying to align everything, if you come up with a design which is random and which can tolerate some impurities like the metallic tubes, if you can tolerate all these and still be able to do communications, that will help improve your system. So in the following figure, a sample communication network where users at a molecular level simultaneously share a random carbon nanotube network bandwidth is shown here. Like, if you look at here, it's not very readable, sorry, but you have several molecular users from user 1 to higher values, and there's a molecular receiver. So the black random lines here are actually showing the nanotubes randomly deployed, as you can see, and the dark red lines are showing the input-output channels or the probes into the media. Like, these are now your nanomachines. They're connected to the medium by using these red bars, and inside these random nanotubes touching each other are providing you your network actually. And your communication is somehow propagated over these nodes. But these are, as you can see, randomly deployed. So each user has a distinguishable impact on the receiver via network interaction, as shown by the range of resistances from each user. So that could be one option. To analyze such graphs, what you need to do is make use of spectral analysis. We'll not go into too much details of spectral analysis, but the spectral analysis in general reveals the topological properties of a graph, such as its patterns of connectivity, and typically involves computing the eigenvalues and the eigenvectors of the Laplacian matrix of a graph. In a nutshell, the spectral analysis is a way of measuring the connectivity of a graph, okay? For the simple explanation. That the Laplacian matrix of the graph is an undirected and unweighted graph without loops or multiple edges from one node to another. And the eigenvalues are related to the topology of the graph, and they represent the specific features of the graph. So, for instance, the second smallest eigenvalue represents the measure of compactness of the graph. A large value implies a compact graph, whereas a small value represents an elongated graph. There are some special cases, like you may have a large eigenvalue, but it could be actually formed in another way. So there are also ways of overcoming such problems, but we'll not go into that detail. Such a spectral analysis is often used for relative comparison of graphs to see, for example, how compact one graph is compared to the other. However, only graphs with the same number of, the line here is missing. I should fix that. I forgot that. The spectral analysis is typically used for comparing how compact the graphs are. So it has been used in a wide variety of applications, like the semantic analysis of documents to cluster documents into areas of interest, as you can see, used also outside the topic of nanonetworks, or comparing structural, functional, and evolutional similarity in RNA molecules, connectivity on the internet, social networks, and others. So though they're very elegant, there are also some limitations to this technique, like Mihail and Papadimitriou argued that when you have randomly generated graphs that satisfy a power law distribution, then the spectral analysis of the adjacency matrix will just produce the neighborhood of high degree nodes and its eigenvectors, but it will miss any embedded structure. But if you have such skewed graphs, then spectral analysis is an efficient tool that will reveal inherent embedded structures within the graph. And even for graphs with such skewed degree distributions, you can apply transformations to get rid of that skewness so that spectral analysis can still be used. And the graph spectral technique precisely will solve the problem of determining the resistance through the network of random tubes in that figure we saw previously, and that can be applied to the analysis of the nanotube graphs to reveal their inherent structural properties. And the impact of the scale on a traditional communication network is typically considered as the network is scaled down to the size of the carbon nanotube network. And from a network perspective, the change in capacity and specifically in bandwidth is more of concern to us. So if you look at a simple harmonic oscillation, which will determine actually the bandwidth of our communication, the harmonic oscillations increase with the reduction in scale. So the potential bandwidth will increase since harmonic oscillations are increasing. The frequency will also increase, and you'll be able to achieve higher bandwidth. So the increase is 1 over L, where L is a linear scale dimension. And the capacity now for J transmitting to I, for a link where J transmits to I, is given by Shannon's formula, as you know. And when you consider all possible multi-level and multi-phase decoding techniques, Shannon says the theoretical maximum rate of clean or close to clean data, that means with low noise, with a given average signal power that can be sent through an analog communication channel subject to additive white Gaussian noise, is defined as bandwidth times ln of 1 plus SNR of that link between I and J. So the term bandwidth is the bandwidth of communication, which determines actually the capacity. And SNR is the, as we said, the signal to noise ratio of that link between I and J. And SNR measures the ratio between the noise and an arbitrary signal on the channel. So when you look at this figure, you see that the channel capacity is higher when you're working at the small scale, but as the scale increases, the channel capacity drops significantly. So this is the case for where SNR is 1 over 2. So in addition to the increased bandwidth potential, the nanotube density also allows for an increase in the number of bits per square meter. So considering a wireless network of today, a typical bit meter per second capacity is limited in the case of traditional wireless networks. And the maximum wireless capacity approximation in a wireless broadcast media can be used to determine the collective capacity. If I'm not wrong, sorry, there's more. So if you consider a perfect distribution mechanism where all links are used as efficiently as possible, that's the best possible case, to disseminate the route update information, a network that has n nodes spread over an area of A, and each possible connection has a capacity of W. If delta is the guard distance to ensure that channel transmissions do not overlap, which means transmissions do not cause interference on each other. They're perfectly spread in the area A. The maximum wireless capacity in bit meters per second is given as in here. Okay, which was also derived in chapter 1. So when you try to generalize to a uniformly random distribution of n sensors over A, which are, as we said, perfectly distributed, the density in that case would be A over n, and the expected nearest neighbor distance would be square root of A over n. And the total distance that the data must travel would be, the expected value of the distance would be the summation from 1 to n of that square root of A over n. So considering a nanotube network, a point source could radiate the information in an omnidirectional manner by the tube structure, of course limited by the degree of the compactness of that tube network. That's where the compactness comes into play. So if the tubes could be well aligned, and then the notion of a guard distance would be unnecessary if you can align them properly so that you don't have that interference. You don't need to consider the interference. And the macroscopic source, a macroscopic source is assumed to generate the data in an omnidirectional manner. So a microtubule will be, is, as you know, at the order of 8 to 25 nanometers in diameter, whereas the carbon nanotube is much smaller at around 1.4 nanometers per diameter, in diameter. The communication capacity in case of the carbon nanotubes radiating compactly from such a circular source is shown in the next figure here. Essentially, the limit is reached as an extremely large number of tubes are joined to the source without any overlapping. But unfortunately, the current technology at the moment does not allow such alignment of the tubes. Okay? So we don't have, the current technology does not allow us to do it for the moment. So there will be an upper limit to the capacity at the moment. That would conclude chapter 4, and that would be all, as I said, for this semester. So in this semester we tried to discuss the general concepts in nanonetworking. This is a brand new field, and as you have seen, there are many different approaches which require background knowledge in computer engineering, electrical engineering, biology, chemistry, and a little bit mechanics also. We even touched civil engineering slightly today, but we can ignore that part. But this is really an interdisciplinary field. It is not possible for you to govern all of these concepts, of course. So the aim of the course was just to introduce you what is being done in this field and what are the trends, so that you pick the one you're interested in, or which one ever looks more reasonable to you. And once you pick that, you can go into more detail in that field. Okay? So that's why this course was really a little bit from everything, but just to give you, as I said, the basic concepts. There's more into this, but we'll not go into, be going into that. And actually, we won't have the time to do that. So that's all about the lectures. Thanks for everything. And now I will be slightly talking about project 2. It's not a real project, actually. That will be about your presentations. as I told during the break to those of you who are here at the moment, this is the last lecture, so we will not have any class next week, but we will have an additional class during the final exams period for the presentations. And hopefully, if there are no conflicts with your final exam programs, I plan to do it on the 7th of January at 10 o'clock. The presentations will not be in class, therefore they will not be recorded on video, but we will have the presentations at Rumeli Hisarı in the pancake house we call Kale or Gözlemeci, the well-known name among us. I will just show you a few slides about the project now, but the requirement is that you prepare a report and also have the presentation, have the presentation. You have to provide me in electronic form your presentation, your reports, at least by the night before the presentation, that is the night of January 6th, so that I can post them on Moodle, making it available to all of your classmates, because you will be responsible for these presentations in the final exam. So that is about 3 days before the final exam, so please study the lecture notes before that, so that in the last 3 days you also have the time to look at your colleagues' presentations. But you're all supposed to attend the presentations, because you have to do your presentation anyway, and also study your friends' reports. Of course, I will not be going into all details, but you should be able to answer the basic questions about your friends. Okay? So let me briefly explain the second project, or presentations, however you call it. So the presentations, as I said, are due January 7th, 10 o'clock. That's when we when we meet. So it's sharp. But as I said, if there are any conflicts with this, we will try to resolve it. But whatever the date is finalized, that's sharp. For the project, you're going to prepare about 20 minutes of presentation. You can use PowerPoint or Beamer or whatever you wish. PDF file is fine. And you should be writing a written report expected between 5 and 7 pages, which is actually a more detailed version of your presentation. That again is expected either in Word or LaTeX. Of course, I don't need the LaTeX code PDF, what I mean. So the presentations will take place in the Gözlemeci at Rumeli Hisarı, not in class, so they will not be recorded. And I will provide you the directions if you want to go there directly. If not, we will be meeting here and we will go to the Gözlemeci together. So I can give you a ride if you wish. You should have at least 3 references in your report. You may start with the reference I provide. You will see that in the following slides. But that's not a requirement. If you wish, you can start with something completely different on that topic. The report should be a summary of all 3 references. I'm not expecting you to implement anything. This is just a survey. But you should read those references yourself, understand them, and summarize them together. It shouldn't be like, okay, I read 3 of them, and here's the summary of 1 of them. Okay? So it should be all about the 3. So you will need to do a little bit surveying first to find the appropriate papers. While searching for the papers, try to make sure that later on, when you read them, you can merge them into a single document. So there should be some relationship in between. You should submit both the hard copy and also in electronic form I will need the hard copy for myself. I don't want to print for every student. That's why I requested the hard copy. But I need it definitely in electronic form so that I can post it on Moodle. Don't expect me to scan your PDF files and then get the electronic form. Your presentation, your report, and your references. That means whatever paper you use as reference, also provide me that reference. Please try to bring 1 or 2 copies of your presentation for your friends so that they can easily follow your presentation. Since we will be sitting on a table and having also lunch during the presentation, and we will not have a projector at Gözlemeci, so we will be using 1 or 2 laptops at a distance. So having something printed would help the people who are sitting a little bit far. You will be responsible for the contents of these presentations, as I said, in the final exam. Therefore, it's important that you submit your material in electronic form the night before the presentation. And they will be posted in Moodle, as I mentioned. You must send me the topic you select until December 19th, which is next week. So please look at the topics and decide which one you select. Before sending me the topic you want, I would highly recommend that you do some survey and see if you can really find something that's feasible. Okay? Later on, don't get surprised. And send me an email message starting as CmpE59G project topic. Otherwise, it may just go into spam by mistake. So these are the possible topics. If you have something in mind in addition to this, like maybe, for example, I don't have active networks here, but if you want to add active networks, for example, you're welcome to do so, if you're interested in it. So, one is, how does a receptor work? How does it load the incoming messenger molecule onto the molecular motor? Okay? Like you receive an incoming messenger molecule from the environment. It comes at the receptor. How does the receptor take that molecule and put the information on the molecular motor to send it to the center of the cell? Okay? So here's a reference. You may start with this, but as I said, you don't prefer this one and you want to come up with your 3 or more references if you wish. Depends on you. This is just a starting point for you. Another one is the active transport of the carbon nanotubes using motor proteins. Remember we discussed this before. Details of the Brownian motion, how it works. Explain the effect of Brownian motion on the molecular motors. If you're interested in this, 2 students may come together and have a single presentation and the document. So it would be a group of 2, if you wish. How the flagellum works and how do bacteria move using flagellum. So you have to explain through a data communications perspective. Don't take anything, just a paper from biology and explain the biological side of it. The important thing is, I'm going to use this for data communications. How do I transmit information? What's the, for example, the channel capacity or available bandwidth, whatever. From a communications perspective, explain this. Another one could be how the ion channels work through ionotropic receptors, which is also known as the ligand-gated ion channels. For example, consider the calcium ion intake through the cell membrane rather than the intracell calcium pools. Okay, and look into this. Another one is nanoscale active networking. 2 students may work on this. And semi-random nanotube networks. Again, 2 students may work on this. That's all, as I said. But if you come up with a different idea, just send me an email saying, I want to work on this. If you've already found some references, you may also attach those references, saying, I want to have my presentation on this topic. I will just have a look, and if it's appropriate, I'll just say, okay, just go ahead. Okay? So if you have anything in mind, just let me know. Any questions about the project or anything else?
One topic only can assign to one student.
Once again?
One topic can assign to one student only, okay?
Preferably, yes, everybody should have a different presentation. But for the ones where I say 2 students, 2 of you can do it. But if a group gets this, I don't want another group doing the same thing. There are enough topics here.
So how do you do mutually exclusion?
You just send me an email. First come, first serve. You can actually, good question. You can post it, instead of sending me an email, if you want, you can just, I hope you're all registered to Facebook group, so just post it on Facebook so everybody else can see it.
Okay.
So nobody can claim it, as long as Facebook is not hacked. Any questions? Okay. Thanks for attending the course, actually. I know that it's a little bit of a weird course. It's different, so most students would not attempt to take a course which is not in the mainstream, I should say. But I hope you somewhat benefited from this new branch of research here, and it doesn't necessarily mean that you're going to do your thesis on this topic, but I hope it provides you some insight, because you're all graduate students, except one, of course. So I hope it provides you some insight about this new, different field of research. As graduate students, you're not supposed to know only your research field and know nothing about the others. So at least if somebody now tells you about nanonetworking, at least now you have some notion about what nanonetworking means, and hope maybe you understand that you shouldn't be dealing with this, whatever. Okay? Okay. Thanks for your attendance, and hope to see you on 7th of January. Of course, if anybody wants to see me, I'm always upstairs. You can always do that. Okay. Thank you.